So I've got my recording going. So I'm doing 1.5, which is analyzing graphs of functions. Now in college algebra, you basically analyze graphs of functions for like 4 weeks of the class. You were just looking at different types of functions. And so now that's just condensed into just functions in general. We're just having one section here. So come on, change the slide. There we go. So yes, Marty, that is the question. Yes. So the question 5, I'm going to read that out loud for those that will be watching the recording. Use the graph of the function to answer parts A through D. Find the domain and range, find the zeros, determine the open intervals on which f is increasing, decreasing, and constant, and then approximate relative minimum and relative maximum values of f. So I'm going to do an example that goes through all of those. So that should be enough to help you on that problem, because everybody biffs that one up. Usually, most people can get like a little bit of points on that, but yeah, that one's just a difficult one. So that is what I'm going to be going over. So 1.5 is covering that essentially. So first you use the vertical line test for functions, and then find the zeros of functions. Determine intervals on which functions are increasing or decreasing. Determine relative minimum and relative maximum values of functions. Determine the average rate of change of a function, and then identify even and odd functions. So there's a lot going in to 1.5. All of that was, except for, well, you need to do average rate of change. Yeah, pretty much all of that was in college algebra. So you're just like condensing the class. But I'm going to go through basically the key definitions and then do an example that's very similar to the application assignment. So starting with the vertical line test. So a graph is a function if you can draw a vertical line at all points of the domain and the line never goes through the graph more than once. So I've got 3 different pictures here. And so the first one is not a function because it has a vertical line and it hits the graph twice. So that is not, come on, it doesn't want to draw. Okay, it does not want to actually finish and write not, oh, there it goes, not a function. So the key is that if you can draw a vertical line at basically all points or any points of the domain, because if I drew a vertical line here, it is a function because it only hit the graph once. But you have to consider at any point, is there a spot where it will hit the graph more than once? And there is, which makes it not a function. So just because you can only hit the graph once doesn't mean that's automatically a function. You're basically trying to disprove that it's a function by looking for spots where the vertical line test fails. The middle example here, this is a function. So it doesn't matter where you draw your vertical line. Oops. Thought I was still on the pen. Doesn't matter where you're going to hit the vertical line or draw the vertical line. You only touch your graph once. And the third one is also a function because they don't have to be continuous. You don't have to have the functions touching each other. There can be gaps. It's still a function. In that case, we drew a line and it hit nothing, but that doesn't matter because if you draw a vertical line anywhere else, and these are not perfectly straight lines, but if you draw a vertical line anywhere else, you're only going to hit that graph once. So it's okay to go through the graph 0 times or 1 time. You just can't go through the graph more than once. So that's the vertical line test. So next is zeros of a function. So the zeros of a function are all x values where f of x equals 0. So essentially you take your equation, you set it equal to 0, and then you solve. So this example, we have a quadratic. To find the zeros, you would take your function 3x squared plus x minus 10 equal to 0, and then you would solve. Since it's a quadratic, you can solve by the quadratic formula, or you can solve by factoring. This one does factor. So it factors to 3x and x. And then I need to, let's see, if I have 5 and 2, there we go, 5 and 2, and then I need to have it to be a plus 6 minus 5. So that would be, that gives me my plus x. The inside is negative 5x, the outside is 6x. That combines to 1x, and then negative 5 times 2 is 10. So you set each factor equal to 0. So you have 3x minus 5 equals 0, and x plus 2 equal to 0. And then you solve each of those for x. So we would get 3x equals 5, because you'd be adding 5 to both sides. And then dividing by 3, and that's x equals 5/3. So that actually goes with the right side one. Oops. This is very sensitive where I touch it. On the second one, you would subtract 2 from both sides, and you get x equals negative 2. So in order to find the zeros, you need to solve the equation by setting it equal to 0, and then solving with whatever technique you know. If it's a quadratic, then you can factor a quadratic formula. If it's something higher, like a cubic, then you might have to use the techniques from college algebra where we had to do synthetic division. You can also graph it and use a graph to figure out what the zeros are. So on the graph, your zeros are where your x-intercepts are. The downside of doing it by graphing only is that if you have any zeros that are complex values, they will not show up on the graph, because complex valued zeros can't be graphed. So it's always best to find the zeros by solving rather than trying to graph, because that ensures you find all of them. So, oh goodness, trying to make something up on the fly here. Not, let's see. Okay. It is difficult to make up something. Okay, so a complex zero, that has imaginary numbers. So if you have a function where when you solve and you end up with an imaginary number, then that would be something that has no x-intercepts, but it does have zeros. So actually, let me pull up Desmos, because I can graph something here. So I'm going to just graph f of x equals squared plus 5. Okay, so this is a quadratic, but this has complex zeros. There are no x-intercepts, but there still are zeros to this equation. They just are not x-intercepts. So if you were trying to find the zeros by graphing, you'd be like, oh, there's no zeros, but that is not true. There are zeros, they're just imaginary numbers. And so you would have to solve x squared plus 5 for 0. Now, I'm not sure if Desmos actually does solving for us. I'm going to just, if I set this equal to 0, we'll do, no, it's not. What if I try to solve? No, it doesn't think solve is a word. But if you set x squared plus 5 equal to 0, you would have x squared equals negative 5. I wish I could draw on this, but it will not. Oh, wait a minute. Here. I'll take a snip, and then, okay. I'm going to just show my, so x squared plus 5 equals 0. Hold on for a moment while I solve this in a snippet. Okay. So there we go. Well, it's kind of all messy there, but there we go. Okay. So if you set this equal to 0, you'd have x squared plus 5 equals 0, and then you would be solving for x. So I'd be subtracting 5 from both sides to give me x squared equals negative 5. Then I need to take the square root of both sides. So that would give me x equals plus or minus the square root of negative 5. The square root of a negative is an imaginary number, so we pull out an I. So we have x equals plus or minus I times the square root of 5. that is a complex zero. There are two of them there. There's a positive and a negative complex zero. They always come in pairs. So there are two zeros here. They're imaginary because of the I. They're just not x-intercepts because the graph doesn't actually intercept the x-axis. So that's the difference. That's something to watch out for. If you're graphing, you can't use a graph to find the zeros because you might miss that. So solving is the best way to go. The degree will tell you how many zeros you have. So since this is x squared, I should have two zeros. So in here, I had a positive and a negative, so I had two of them. If we go back to the original example here, this also is something quadratic. It's x squared, so there's two zeros, but these happen to actually intersect the x-axis. So they are also x-intercepts. Does that make sense or help for your question, Marty? Okay. So moving on from zeros, we have increasing, decreasing, and constant intervals. This is the part that everybody messes up on the assignment. So a function is increasing over the domain if the y values increase as you move left to right. So when we look at increasing, decreasing, and constant, we always look left to right. When we give when it's increasing, we are always giving intervals of the domain. So you're listing for which x values. A lot of people give ordered pairs. We're not doing ordered pairs. We're giving the x values over which it is increasing, decreasing, or constant. So if you're moving left to right and it's going down, if your y values are decreasing, then the function is decreasing over that section. And then if you're moving left to right and your y values are staying the same, then it's constant over that section. So I'm going to go into this in more detail when I have an example. But you want to remember that you give the x values for these intervals. You are not giving ordered pairs. Next, we have relative minimum and relative maximum values. So the plural is minima and maxima. And these are the highest and lowest parts of a function in an interval. So it's just, is there a peak somewhere or is there like a low part somewhere? It doesn't have to be the max, like the highest or the lowest. There may be something that's higher and that's okay. So for example, I'm going to just draw this function. So I'm going to take, this is a relative maxima, this is a relative maxima, that's a relative maxima, and then these are minima right there. They're not, there's more, you can have more than one minima and maxima. They don't have to be the absolute highest and the absolute lowest. The highest and lowest are called the absolute minimum or the absolute maximum. Relative are just mean in their area, is that a high or a low spot, or in their neighborhood sometimes is a term that's to indicate where it is. These are sometimes called local minimum or maximum, so that sort of makes sense with the neighborhood idea. It's like in your area. Now, the book doesn't actually state this specifically, but when you're looking at relative minima and maxima, you do not include the endpoints. So even if you have a graph and let's say, and this is something like we have on the homework where it's actually closed dot and then it does some stuff. So the endpoints might be the lowest point in that area, but they don't count. So the book doesn't actually specifically state that, but we don't include the endpoint. So we're just looking inside the function itself when we're looking at relative minimum and relative maximum values. And when you're answering these, you can give these as ordered pairs. You could say there is a relative minima at, and then give the ordered pair for that actual highest point or lowest point if it's a minima. And then we've got average rate of change. So the average rate of change is actually just the slope. What you're doing is you have 2 points, and if it tells you to find the average rate of change, you're just finding the slope between those 2 points. Even if we don't have a line, if you connected those 2 points, you have a line, and so that's why you're allowed to find the slope. So just think of average rate of change as just finding the slope, which means you can do this even if it's not a straight line, but that's why they use the word average rate of change. So if it's not a line, we have different terminology for it. And it's called average because the slope will change depending on which 2 points you have. So if I picked 2 points right here, I'm going to attempt to draw a straight line. My line would be steeper than the gray line there. So your slope isn't the same. So that they call it the average because you have to kind of average out over the interval. So we don't call it slope because slope is specific for lines and it's constant, but it's the same formula. It's basically y2 minus y1 over x2 over minus x1. They just use function notation instead, but it's the exact same thing as slope formula. So that line that we're drawing, like the gray line, that's called the secant line. And there are special instances where if the line kind of follows the curve, like the red one that I drew, that is called a tangent line. And this terminology actually will show up if you go on to calculus, where you will be talking about tangent lines. And that's actually the whole idea behind a derivative. So just when you see average rate of change, just find slope. Use the slope formula. That's what you're doing there. And then lastly, we have even and odd functions. So an even function is symmetric with respect to the y-axis. What this means is that if you've got the y-axis is vertical, so it's just a mirror image across that vertical line of the y-axis. An odd function is symmetric with respect to the origin. That one's harder to visualize because it's reflecting over the horizontal and then again over the vertical. It's reflecting in 2 pieces. So it's a little harder to visualize that. So we do have ways to figure it out algebraically. And what you do is you plug in negative x and then you simplify. So if you plug negative x into your equation and all the negatives disappear and you end up with the same equation you started with, that means it has even symmetry. If you plug in negative x and you start simplifying and you end up with the opposite sign of everything that you started with, then it's odd symmetry. And then if it doesn't follow either of those rules, then it is neither. And I have an example where I'm going to go through even and odd and show you the steps for that. So let's get into the examples here. I have 3 examples. So this first one, it's not the same graph as you would see on problem 5 in your homework, your application assignment, but it's similar. It has the same idea. I'm using the word estimate here because we don't have enough grid points to figure out where these values are, so we're going to just estimate based off of the graph. So first is domain and range. So domain. So the domain is the x value. So I have to figure out where my x value is. And so it looks to be about there. So reading the tick marks, I know that this is -2. So since my tick mark that I drew there appears to be halfway between, it looks like it's at -1. And it has a closed circle, which means that value is included. So that my domain is starting at -1 with a bracket. And then, oops. I have graphs, like everything to the right here, I have functions on my graph. Now, if there's no circle at the end point, we assume that this goes on forever. So I'm going to assume that the graph goes on below what I have here. So we're actually going towards infinity. Oh, this is very sensitive right now. Oops. So it's going towards infinity here, towards the positive x values. So my domain would be from -1 to infinity. And with infinity, we always use a parenthesis because we can't actually reach infinity. So you can't touch it. It's not. So that's why we're curving around it. That's how I remember which symbols to use. So that's the domain. For the range, we're going to do something similar, but we're going to look at the y values. So I need to figure out what my highest and lowest y values are for the range. So the highest value looks to be around here, which we can call that 7. It's between 6 and 8. We can say that's 7. So that looks to be the highest, and then everything is below, and because of that arrow, it goes on forever. And when it's going down, that's going towards negative infinity. So when we write our range, we're always going from lowest to highest, just like domain goes from lowest to highest. So for the range, I'm starting at the bottom and then going up. So I'm starting at negative infinity. So since we can't touch negative infinity, that's going to have a parenthesis. And then we're going up to 7, and then that has a bracket because 7 doesn't have an open circle. So that's part of the graph that is included. So that's the domain and range, and we're just estimating by the graph based off of what it looks like. And usually when you have to estimate like this, estimating whole numbers is best because that's just a lot easier to work with. So do you guys have questions on the domain and range part for this example? Okay. So next is the intervals over which the function is increasing, decreasing, and constant. And this is the part that a lot of people get confused. So again, I'm going to draw. So let's start with increasing. So our graph is increasing in just one section here. But I need to translate to what x values is that increasing. So I'm going to draw, let's see. Let's just say that's from 0 to 2. So between x values of 0 and 2, that's where we are increasing. So you're not writing ordered pairs. You're using interval notations and open intervals, so we're always using parentheses. So it is increasing, whoops, that is an alpha, not a, from 0 to 2. Or you can think of it as x is between 0 and 2. So we're not doing ordered pairs. We're saying what values on the x-axis and what section of the x are we increasing. And so we're increasing between 0 and 2 on the x-axis. And then when we do decreasing, it's the same idea. So we have two sections where we are decreasing. And so one of them appears to be at 2. And then here we've got from like 1 to 0. We're just estimating here. So my decreasing, so I'm looking at the x values. So one section I'm decreasing from -1 is 0. And then I'm decreasing again from 2 to infinity. Oops. Again, very sensitive because this is going on forever and it's just going to go down forever. So, yeah, it's like I just touched it a little bit with my hand. Then it's, okay, let's try this again. 2 to infinity. So those are the values of the x at which it is. So we're not looking at the y values. We're not writing orders. We're indicating which parts of the domain is it going down. So I like to kind of translate my pictures and kind of flatten them onto the x-axis so I can see, okay, what parts I'm actually decreasing, and then that's what I read it off. And then it says constant. So you do have to specify that there are no constant intervals, because think of this when I'm grading. If it asks you for where it's increasing, decreasing, and constant, you give me increasing, decreasing, and you don't list constant, I don't know if you listed, like I read that and I'm like, did they just forget to do constant, or do they recognize that there's no constant interval? So you have to specify that there's no constant interval so that I know that you haven't just forgotten that. So that is specific to the assignment, because the assignment, I'm going to let you know there are no constant intervals, and so you need to make sure that if there isn't any intervals, you need to tell me that so that I know that you didn't just forget to answer that part. So that's the increasing, decreasing, and constant. Do you guys have questions on that and how to write those or how to figure those out? Okay, so Brianna says no. What about you, Marty? Another example would be nice. Okay. So let me draw something. Let's see. And then I need to mark where these are at. So, okay. So let's just say the high and the low point are at -1 and 1. And I have this graph in blue. So let's look at the increasing. So I am increasing. It's not a perfect graph, so I'm increasing here and again over here. I want to look at the parts of the domain. So if I flatten this and it goes on forever, that's going to be here and then here. So I'm going to attempt to, oops, that erased too much. And I don't know how to undo that. So let's try to draw that back. Oh, goodness. What's the increasing? So it's increasing to here, and then it was going down. Oh, I messed it up. Okay, let me redraw this. This is a mess. Once I lost my graph, it was like, oh no. Okay, let me redraw and try not to erase it. Okay. All right, so that was at 1. That's at -1. Okay. And then, so it's increasing from -infinity to -1. And then again from 1 to infinity. So if you look at your ordered pairs, this point right here is 1 comma, let's just say -1. I'm just going to make that up. And then let's say this is -1, 1. So you're looking at the x values. At what parts of the x is it increasing? And so, Brianda, you're correct. So we're going from -infinity to -1. And then it's open interval, so we have a parenthesis. And then it's also increasing from 1 to positive infinity. So you're looking at your x values if you're using your ordered pairs as kind of your cutoff points. Decreasing is now going to be the missing part in between because we don't have any constant intervals. So we are decreasing in between here from -1 to 1 on the x. That's where we are decreasing because that's where our graph is going down. So we are decreasing from -1 to 1. And then we have no constant intervals. So if it helps you to label the points where you're changing direction, you can do that, but you need to look at the x values when you're naming these not the y value. It's the x value that you use to get your intervals. Does that help? Okay. So that's our second example there. And then next on here it says estimate the relative minima and maxima. And so the endpoints don't count. So I'm going to erase what I have on my graph here so that I'm going to just point it out here. So my low point, that would be a relative minima. Or a minimum because there's just one of them. And so if I have to estimate that ordered pair, okay, it's not exactly at 0. Let's say -1/2, and let's say that's maybe 2.5. I'm just estimating here. So I'm just giving the ordered pair where the relative minimum occurred. Another way to write it is to say the relative minimum is 2.5 at x equals -1/2. I think that's a little confusing, so writing it as an ordered pair and then just labeling that is the relative minimum, that is fine. And then we have a high point right there, and that is the relative maxima. If you're estimating, decimals are fine instead of fractions. If they give you the points exactly, if these were actually labeled, then use what they give you. But because I'm just estimating here, you could use 0.5 and 2.5 if you want. Because it doesn't say. So I'm just guessing, and I work with fractions a lot, so I just write it as fractions. So, so now we need to estimate that maxima, the maxima point there, which I think is about 2.7, roughly. And so that's a relative maxima, and that is actually also an absolute maxima because that's also the highest point everywhere on there. So that is both a relative and absolute maxima. I'm going to just abbreviate that as max. So that is the relative and absolute max. And then we have a relative minimum, but that's not the absolute minimum because we do have numbers that are lower than that. Yeah, so a sine wave. So that's an interesting thing because it does have an absolute lowest point. It just occurs more than once. So it is possible to have more than one absolute minimum if they're all the same value. And it would be the same thing with the maximum. So it depends on, that is something that you'd have to look to see how absolute minima and maxima are defined as far as your textbook, because some textbooks are not consistent on their definitions for something like that with a sine wave. So that actually comes up more when you get to calculus, because when you get to calculus, there's actually a formula to find these, and you actually take the derivative to find minimum and maximum. Are there any other questions for this example? Okay. So here I have one where we're going to determine if the function is even, odd, or neither. And so we're going to do this algebraically. And so the rule is you plug in -x into your function, and then you see what happens. So I'm going to plug in -x everywhere I see x. So instead of x, I have -x, and then my square root, then 1 minus -x squared. So this is how you test whether it's going to be even, odd, or neither. So everywhere I'm seeing my x, I need to replace that with a negative version of it. And then you're going to simplify, and you're going to simplify the right side and see what happens. So I have a -x in front of my square root, and then I have 1 minus, and then If you're squaring a negative, that always comes out to a positive. So that's going to end up with a positive x squared because a negative 1 squared is a positive 1. So now I have negative x times the square root of 1 minus x squared. Now if you're looking at this, we have, if we ignore that negative in front, everything else, this x times the square root of 1 minus x squared, that is the same thing we started with. That is g of x. So I just have a negative and then I have g of x. So this is really equal to negative g of x. So I just got the same function but just with a negative in front. So what I have here is g of negative x equals negative g of x. When that happens, that means that this is an odd function. So when you plug in a negative and then you basically get the opposite of what you started with, that's an odd function. So I want to pull up Desmos so I can graph this function so you can see what it means to be odd. So g of x equals x times the square root of 1 minus x squared. So this is what it looks like to be symmetric across the origin and to be an odd function. Is if we look at the left part, if you flipped it as a mirror image across the x and then flipped it again across the y, you get the right side. So let's see if I take another screenshot of this. Snipping. Oops. No, I'm going to get the wrong snip. Okay, hopefully this is snipping the right part. I want to snip here. So we have this part right here. If we reflect that across the x, so I'm going to try to do that in a different color, and it's probably going to come out really badly. It's going to look sort of like, pretend that's a perfect reflection. It's not perfect. So that would be, we reflect it across the x-axis and we get like a mirror image there. And then you can see that reflection is a mirror image across the y. So that's what makes it odd. It's because if you reflected it and then do another reflection, it matches the other side. So that if we reflected the green across the y, it would match the red part, and then we get the entire function. Hopefully that kind of makes sense, but that's what an odd function looks like. It's sort of like a reflection over two different parts. And so that's odd, and we can test it with the equations. So do you have any questions on that? Okay. Awesome. All right, so pulling back. The last one here, this is one we're going to graph, and we're going to graph this using Desmos. Actually, this one I can graph without Desmos because I know my transformations. But it says to graph the f of x equals the absolute value of x plus 5, and then determine the intervals for which f of x is greater than or equal to 0. So I'm going to graph this absolute value. So an absolute value, f of x equals the absolute value of x. When you graph that, it is a v centered at the origin. If you have x plus 5, that is shifting 5 to the left. So now it's centered at negative 5 on the x-axis. So it says determine the intervals for which f of x is greater than or equal to 0. So that is where your y is greater than or equal to 0. And so when it says the intervals here, it's looking for the x intervals. Where on the x is our y value greater than or equal to 0? So this is similar to the increasing decreasing question, except that now we're just looking at where is it above the x-axis. And so, okay, so Brianna, you were saying you're listing 0. And you're saying, okay, you changed it to always. Yeah, it is always greater than or equal to 0, our graph here, because it's always above the x-axis. So if I was to just highlight the sections where I'm above 0 for the y, I'm above 0 here, I'm above 0 here, and it goes on forever in both directions. So our interval for which our function is greater than or equal to 0 would be -infinity to +infinity, because it's always greater than or equal to 0. So this is a hard one because it's asking about where your y is positive, but then you're given the answer for the x values, not the y values. So it's the same sort of idea with the increasing, decreasing, and constant, is you're looking for where your y is increasing or decreasing, but when you give your answer, you give it in terms of the x. And so that's confusing for a lot of people, but you have to do this when you get to calculus. This example is something that you often have to do when you're in calculus. So that's why I wanted to make sure that I went over an example like this to clarify what it means when you're looking for intervals, and then also so you see something that comes up in calculus. So do you guys have any questions on this third example? And actually, because I have this nice graph here, I'm going to just throw in the decreasing and increasing. So this particular graph is increasing from -5 to infinity when you're looking at your x values. And then it is decreasing from -infinity to -5. So that's the decreasing section. So we look at these in terms of x values when we're listing these intervals, not the y values. So this one's a little bit easier, I think, to look at the increase and decreasing, because you can see it's a little clearer to see where they change. It's clearly at 5. It goes from decreasing to increasing. So that is, uh-oh. Oops, I accidentally unplugged my other screen. That's okay, because that was all I had left for you guys. So I accidentally unplugged the screen you guys are seeing, but that's okay. So do you guys have any questions in general on anything that I went over, or maybe other things you've encountered in chapter 1, or maybe on the application assignment? Okay, we got we got a no and a not yet and a no. Okay. Even though you guys didn't ask about this, question 2, where it says to estimate the value between like 40 and 50, show your work or explain how you got your estimate. So when you give me whatever your estimate is, tell me how you got that. And then where it says to compare your answer to the actual function values, make sure you actually give me the function values, and then you compare it, like saying if are they larger, smaller, that sort of thing. Because usually a lot of people either don't tell me how they estimated. So for me, I can't evaluate whether it's a good estimate or not, or they won't show their work, or they would forget to compare. And so just for problem 2, that's usually where the other spot is that people lose points, is for that one. Estimate are not a graded expectation. I'm not sure what you mean there. You could elaborate. Okay, if you guesstimated 5, Well, explain how you got that number. So tell me what made you decide that your estimate was at 5 or whatever. There is a specific method that you should be using, or based off of, yeah, the 40 and the 50 actual, no, okay. So, but like, how did you come up with 5? That's the word. Has to be in between. But how did you know how much in between? So that's where I'm trying to get at, is you need to be very specific about how you determined, where it was in between the 40 and the 50. Um, because they're having you estimate like 45.5, and 45 is halfway rough, you might want to say, okay, well, if 45 point, okay. So you don't want to plug in the numbers instead of guessing, because that defeats the purpose of the question, because of course the question does say to estimate. But since it says 45.5, which is close to 45, and 45 was halfway between. So maybe you might want to think about doing halfway in between the 40 and the 50 numbers for your estimate. And then the next part, you actually find what the exact values are. Because you don't want to use the exact values to guess, because then you're kind of doing things backwards. I see, going on. So you do want to try to explain as much as possible, because a lot of these application assignments, there are multiple ways to show your work. And so in order for me to completely follow what you do need to try to show as much work as possible, or explain what you're doing, because there are multiple ways to do some of these. It's not so much this week, but some of the later weeks, there's more than one way to do some of these problems. And so you need to basically prove to me and show me what you did by showing all the math. It's when you start getting into applications and pre-calculus, it's not as clear cut as algebra was, so it's a little harder to grade unless you have to prove to me stuff. So that's all I wanted to make sure I told you guys about the application assignment. I have scheduled the introduction to week 2 for 2 o'clock, I believe. I had my calendar up. I have too many. Nope. Bring up my calendar. Oh, I did have it up. I must have accidentally closed it. 1 o'clock. Okay. I will be doing evenings. So, yeah. So the week 2 introductions at 1 o'clock. So I am doing live sessions for 3 courses, and according to the survey, everybody is available at the exact same time. So I can't do live sessions for everybody at the same time for 3 different classes. So I'm rotating through. So I will be rotating. You guys will get evening sessions for like an introduction, but I can't guarantee that, because I need to try to make sure that everybody out of all my 3 courses has a chance to do evening times when everybody's available, because I'm only one person. And so, and I'm also doing live sessions for the September classes as well. So I'm like, I don't have enough time. There's not enough of me to do evenings for everybody. So I don't have an evening for the introduction this week, but yeah, and if you're 2 hours behind, that's harder too, because then, most people we have are actually in Eastern time. And so then I'm trying to, yeah, it's a mess plan these, but all of these, I'm trying to give, I will have some evening times. There will be some day. I do have, so I haven't done live sessions for calculus at all, because I have not taught the Calc 1. They usually have me only doing Calc 2. So, and they like to have me doing the algebra courses and pre-calc. So I have live sessions from all of the fundamentals of algebra courses and the college algebra courses, and then pre-calc, but I don't have anything for going higher, because last time I taught Calc 2, they just recently revised it, so I'd have to start all over, because they've changed books and everything. So, but anything that I have saved that's not for pre-calc would be found on my YouTube channel. The stuff that's linked in the classroom, I have only the pre-calc stuff that's linked in the classroom. Any other questions, comments? If you're signed up to Remind, you'll get a reminder when I have this video posted and processed and all that. And then when I send things through Remind, they do go to everybody. So I sent a reminder in one of my other classes, and they thought they went to the individuals, and I was like, no, these are announcement sort of things. They're going to everybody, so I'm not singling anybody out. So if I send a reminder like, oh, work is due, that doesn't necessarily mean it's you haven't turned in work. Just it's a reminder for everybody. So just that's what that's for. All right. So if you guys don't have any more questions. Yes, and all the links are saved, so that, yeah, that's why I record these, is because I know that with the scheduling it's hard. So yeah, they're all saved, they're all in the classroom, or going to put in the classroom under the live session link or the instructor video link. They're all going to be on YouTube. I'll be putting them through Remind, so you'll have access to these if you can't attend live, but I'm trying to get a good mix of times. So all right, so thank you guys so much for attending this live and asking questions. It helps me improve so that I know, oh, these are questions people have. So now next time I teach this, I can anticipate those questions. So you're helping make my explanations better by actually attending live and asking questions. So I appreciate it. So if you guys have other questions, of course, you can just email me, or you can reply on a Remind, and those replies come only to me when you send a reply. And then if I reply to you via Remind, that only goes to you. But if I'm just sending out a blast, that goes to everybody. So you're welcome to contact me via Remind if that's quicker for you to like send text through there or something. That's fine. So yeah, so that's it. So will it accept a photo of a problem? That's a good question. I would say give it a try. If I can send files out, I would imagine you should be able to send me files back. So I would say give it a try, send me a photo, and then I'll take a look and see. Because that would be really handy. If you can send me photos through there, then if you're stuck on a problem, you can send me a picture, and then you don't have to try to email it. So we'll find out. We'll experiment and we'll see what it does. So, all right. Well, I will get the recording off so I can start this processing and getting everything on YouTube and all that fancy stuff. So I will see you guys later. Hopefully Wednesday if you can attend, if not at our next evening session. So you guys have a great night and enjoy the rest of your Monday.